the Epic of Gilgamesh, 2000 BC, we see one of the first appearances of what a rainbow means. Divine promise after a catastrophic flood. Norse mythology, the rainbow bridge Bifrost connects Midgard, Earth, to Asgard, the realm of the gods. Ancient Greece, 4th century BC, Aristotle provided one of the first serious, though flawed, explanations. In the Roman Empire, 65 AD, Seneca the Younger's theory noted its appearance opposite the sun and in water sprays. A rainbow mainly consists of two parts, refraction and total internal reflection. Refraction. What is that? When light goes from, say, air to water, the speed of light slows down. In other words, in air, where light travels at 3 times 10 to the 8th meters per second, when it traverses to water, the crest and peak of that light wave tend to slow down. This ratio of the speed in water to air is known as the index of refraction. We call it that because it refracts, bending towards the normal, an imaginary line that runs perpendicular to where that light hits the boundary. If there was a tank moving on concrete, going quickly, and shifts into something where it moves slower, like mud, if it's moving at an angle, the tread that hits the mud first will slow down, causing the tank to steer a little bit before both treads are on the mud where it can continue straight, just traveling slower. Snell's law. It tells us the relationship between the speed of light, the angle at which the light makes in that medium, and the index of refraction. The slower the light is, the lower the angle will be, the larger the index of refraction. So why do different colors separate like that? The amount that light refracts depends on its wavelength. Each color of light, red to violet, has a different resonant frequency, a natural frequency at which the atoms and particles oscillate. Light waves with frequencies closer to these natural resonances cause stronger, more energetic oscillations in the electrons. This stronger interaction effectively slows down the light more than waves with frequencies far from resonance. High-frequency light, like blue or violet light, interact more strongly, slows down more, and thus refracts more. Lower-frequency light, like red or orange, interacts more weakly, slowing down less and refracting less. This frequency-dependent bending is why a prism splits white light into rainbows. Blue light bends the most, and red light bends the least. The critical angle is a specific angle of incidence where light, moving from a denser to a less dense medium, refracts at exactly 90 degrees. At greater than 90 degrees, instead of passing through the boundary, the light is simply reflected back. Therefore, total internal reflection. You can observe this in a pool. Looking up, you see the world outside the pool compressed into a window of light. Beyond this circle, you see the reflection of the pool's bottom and sides. Because of the shape of a water droplet being mostly spherical, light reflects, allowing us to see the different colors. This brings us to the last point. The sun must be behind you in order to see a rainbow. Sunlight must enter raindrops in front of you, bend, bounce off the back, and bend again as it exits back towards your eyes. But the wonder remains. Science without humanity is lame, and humanity without science is blind. There is mathematical reality woven into the fabric of the universe that you share with winding rivers, towering trees, raging storms, and the prettiest of rainbows.